欢迎就是我的今天 A 的角色 Vladimir。
Well, hello everyone. Can you hear me well? Okay, nice. Thank you for attending my presentation about embedding V8 in NativeScript. I'm Vladimir Mutafov. I'm part of the NativeScript runtimes team at Progress. And today I'm going to tell you about how we embed V8 in NativeScript, how we use it, and what for. So let's start with an introduction. Do you guys know what NativeScript is? Somebody? So basically, NativeScript is yet another framework for building cross-platform mobile applications. It is something similar to React Native or Flutter, something like that. And in NativeScript, we can use frameworks like Angular, Vue, or plain JavaScript, TypeScript in order to build mobile applications, both targeting Android and iOS. So yeah, we can use JavaScript for building mobile applications. And let's take a look at the architecture of the NativeScript project. At the core, of course, we have the Android and the iOS operating systems. Above them, we have the NativeScript runtimes, one for Android and one for iOS. Above them, we have a common cross-platform abstraction, which includes different layouts, UI elements, and CSS for styling our applications. And this abstraction is used for example, creating buttons. We do not need to create a different button for Android and a different one for iOS. We just use the NativeScript abstraction to create one button, which would look natively on both of these platforms. Above that, we have a simple application framework, the NativeScript one, which includes data binding, navigation, and stuff like that. Of course, we can use Angular and Vue. As of now, the community of NativeScript has even provided such support for frameworks like React or Svelte, if you have heard it, but mainly NativeScript is nowadays used with Angular or Vue. Today we're not going to talk about the abstractions and the higher level APIs. We are going to focus a little bit about the runtimes, and more precisely about the Android runtime. We'll see how it works internally and how it's made. So one of the main benefits of using NativeScript is that we can use native APIs like Java classes or Kotlin classes and interfaces and stuff like that. We can use them in JavaScript as if they were regular JavaScript objects. To achieve this behavior, many things happen under the hood of NativeScript. So let's see what the NativeScript application package consists of. We have our Android phone and we have the Android application. At its core, NativeScript applications are packaged like regular Android ones. However, we have some NativeScript magic inside of it. And what is this NativeScript magic? Well, we have the user's JavaScript code, which consists of the business logic of the application. And we have the NativeScript runtime, which could be considered as the bridge between JavaScript and the Android world. And we should probably talk a little bit about executing the JavaScript. Well, in NativeScript applications, the one who executes the user's JavaScript code is V8. It is the same JavaScript engine as used in Chrome, Node.js, and many other open source projects. The reason why V8 has been chosen as the default execution engine of NativeScript.tw is that it provides exceptional execution speed. And it has a pretty nice embedders API too. We're not going to talk about how V8 works internally. We're not going to talk about the internals of modern JavaScript engine, how it interprets the JavaScript, how it compiles it, and how its garbage collector work. But if you want to understand the internals of JavaScript engines, perhaps these videos are something you could find interesting. So we have V8. And let's take a look at an example how we can use a native API through JavaScript. So you can see that we're trying to instantiate some media recorder class. But we haven't defined this stuff anywhere. How does it work and what is that actually? Well, to understand this, we have to look into one of the build tools triggered when building NativeScript applications. When a NativeScript developer starts building its NativeScript application, he may choose to include native libraries. Those native libraries are, for example, the Android SDK and anything which could be used in a regular Android application. So when he starts building his application, the metadata generator tool is triggered. Its goal is to parse every such native library and collect information about all the Java or Kotlin classes, interfaces, methods, fields, types, and stuff like that. Collect this information and store it in a compact binary format, which would later be used by the NativeScript runtime. So from the example, we can understand that these stuff are some metadata representing some types in the native world. But how do we actually use them? Who allowed us to use them and how? Let's see what happens when we launch our NativeScript application. So we initialize V8 at startup and we tell it to load some scripts and execute them. We load our metadata and we attach some callbacks. But what are those callbacks? I mentioned that V8 has a pretty nice embedders API, and this API allows us to create functions or objects and attach them to existing V8 objects. So, for example, if we want to create an object through C++ and attach it to V8, we first have to get ourselves a V8 isolate and a context. I'm going to describe what isolate and context are a little bit later. But as of now, you can see that we are getting the isolate, we are getting the context, and we are getting the global object of the context. After that, we are creating an object template. An object template in V8 terms is the blueprint of an object. And after that, we use the set API on the global object in order to set some object inside of the global V8 object. And in this case, we attach our custom object to the global one. And every time somebody accesses global.ourCustomObject, he would receive the object we have defined a couple of rounds later. And yeah, this is how we could use the V8 API to create, for example, an object. Same goes for creating functions. We don't have the object template, but we have a function template. And we could register some callback, which would be invoked every time somebody executes our custom function, which is set again on the global object. And those are two pretty simple examples how we can use the V8's API in order to receive callbacks if somebody accesses some functionality. And something similar is happening in the NativeScript runtime. So let's get back to our example. When we access the Android package, it is something that is considered a top-level package. Top-level packages are something like Android, Java, COM, org, or something like that from the native world, which has been attached to V8's context initially when we start all the NativeScript runtime. So when the application launches, we have parsed the metadata, and we have set, for example, this Android object on V8. And whenever somebody accesses some property on the Android object, for example, media, we query the metadata, and we find that media is yet another Java package. So we return a proxy object which has some properties, again with some callbacks. And when somebody accesses the media recorder property, for example, it is found in the metadata, and it's found that it's a class, it's not a package, it's something different. So in those cases, when there is a class or interface coming from the native world, we expose it as a JavaScript proxy and return a constructor function. But this function is something magical. And what is magical behind it is that it again has a callback. This time, we call this callback a constructor callback. And every time somebody tries to create an instance of the media recorder, this callback would be triggered, and again the execution would be delegated by V8 to our NativeScript runtime. And in the NativeScript runtime, we have to instantiate the native object in the real Android world. But how do we do that exactly? Well, we use JNI. JNI is a mechanism used in the Java virtual machines and the Android runtime as well. It allows C++ code to call into the Java world and vice versa. So in our case, it could be considered as the bridge between V8 and the Android runtime. And we use it to create programmatically an instance of the desired object. So after we have created the native object and stored a reference for it in the NativeScript runtime, we create a JavaScript proxy object. The proxy objects are something similar to the native class. However, they are created in the JavaScript world, and they have the same properties. In our case, when we return a proxy object, it has the same properties as the native media recorder class would have, the same fields, the same methods. We return that to V8, and for example, if we want to access some random field on the newly created instance, we receive a field getter callback from V8. And after that, we search into the native object to find this property and see what its value is. But there's a slight complication. We see what the value is, we know it, but the Java types and the V8's JavaScript types are not the same. For example, the Java string object is not the same as the JavaScript one. And perhaps it could be easier for users not to have to manually marshalize these kind of objects. And for that, we have the marshalling service in the runtime. Its goal is to marshalize every primitive Java type to the corresponding JavaScript primitive type. This means that for, let's say, Java integers and doubles are translated to JavaScript number type. Same goes for strings. However, the objects are translated a little bit different. Java objects are translated to JavaScript proxy objects and returned to V8. Accessing a native method through JavaScript is pretty much the same. We receive a method callback, and the NativeScript runtime calls the method on the original Java object. Again, the result is marshalized and returned to the JavaScript world. Probably all those callbacks have confused you a bit by now, so let's see what happens initially when we instantiate the media recorder class. V8 would trigger our constructor callback, and we would instantiate the native object in the Android. After Android returns an instance, we then create a proxy object and return it to V8. Accessing methods is pretty much the same. As you can see, we get the method callback and invoke the original method on the native Java instance. After we have a response, we return it to JavaScript, martialized. And we saw how we can use native APIs. We saw how we can create native objects through JavaScript. But who owns these objects and who ensures that we have no memory leaks and who deletes all this stuff after we have done using them? Let's talk a little bit about garbage collection. Perhaps most of you know that JavaScript is a garbage collected language. This means that unlike C++ or C or Rust, we do not need to explicitly free the memory we have used. So somebody else does the job for us. And this is the garbage collector of V8 in our case. And the Android runtime has pretty much the same garbage collector. Again, its goal is the same. It has to unallocate memory which is not used anymore and understand which objects are not used anymore. What is bad for garbage collectors is that they're non-deterministic. We do not know when the garbage collector would run. This depends on the virtual machine, the runtime itself, and we do not know when it will start. So this creates a problem in NativeScript. We have to ensure that both of these garbage collectors are synchronized. And no object from JavaScript, for example, is prematurely garbage collected when it shouldn't be, when it's still used by the native side. And of course, this is the same for native objects. We should not let native objects die before finishing their use in JavaScript. So how is it done in NativeScript? Well, we depend strongly on the V8's finalizer callbacks. The finalizer callbacks are something which V8 would trigger every time it considers an object to be dead on its side. And we do some stuff with these callbacks when we receive them. And as for the native objects, initially we store strong references for all of them. But let's see how it goes. When we have created the media recorder object, we have the Java objects on one side, and we have the JavaScript proxy object on the other side in V8. Initially, they have a strong reference. They are held together, and nobody can remove them now. But what happens when the garbage collector kicks in? So let's start with the V8 garbage collector. When it considers the recorder object to be dead, it fires the finalizer callback, and after that, we remove the strong reference and transfer it to a weak reference. The strong and weak references are held by the NativeScript runtime in some internal collections. And after that, we tell V8 not to collect the object because it's still in use. And when the Android garbage collector comes in, it sees that the recorder object has no longer a strong reference. It sees a weak reference. And the difference between strong and weak references is that when the Android garbage collector sees a weak reference, it could safely remove it. But if it sees a strong reference, it could not delete the object safely. So in our case, we now have a weak reference, and Android could reclaim the memory. When the next V8 garbage collection occurs, we see that there is no value next to the weak reference after the finalizer has been triggered, and we could say to V8 to safely remove the object. However, there are some challenges. In some cases, we could run into out-of-memory exceptions. Although this is rare, because of the fact that most of the objects are pretty small and are garbage collected just in time. When dealing with native arrays or native images, we may run into some of these problems. And this is because collecting some native object instantiated through JavaScript needs several GC cycles in order to be deleted. And such example, as I said, is when we create a big image through JavaScript. So it's big, but it's big only on the native side. The JavaScript proxy object is pretty small, and V8 would probably consider it would probably not start a garbage collection because of it being so small, and it would not sense the pressure of the external native memory. And this is a problem because storing so many native images in JavaScript, perhaps we would run out of memory in some cases. And what could we do in such cases? Well, there are several strategies. One of them, implemented in the NativeScript runtime, is to call a special V8 API, which tells it that there is some external memory, and it hints V8's garbage collector to be triggered more often. There's another strategy through JavaScript to call several garbage collections. The V8's garbage collector, the Android garbage collector, V8 garbage collector again, but perhaps you see the problem. This is really not a useful strategy, because internally it's not guaranteed even if the garbage collector would start. And of course, it is not a cheap operation. We should definitely not invoke garbage collections like that. So how about we don't do that? In such cases, when we have big native images or native arrays, or every object we could consider a big one in the native world, we could use the release native counterpart function. It is provided by the NativeScript runtime, and what it does is, when provided a JavaScript object, it removes the strong reference held in the NativeScript runtime. So when the Android garbage collector kicks in, it would see that we no longer hold any references to the native object, and it would delete it. So let's talk a little bit more about multi-threading now. All of you know that JavaScript is actually a single-threaded language. There is no concept about threading in the language specification. And in the case of NativeScript, JavaScript is also used in a single-threaded way. And the single thread which is used is the user interface thread. It's the main thread in Android. But this may have some problems, and let's see how we have dealt with them. Building mobile applications, we should consider the fact that we should run in 60 frames per second. And this means that we should draw a frame every 16 or so milliseconds. And failing to meet this budget, we create some junk, some lag, some stutter. And this is quite visible in the following video. You could see that 60 frames per second is pretty much better than 15 or 30 frames per second. And as for 120 frames, well, you could see that it's even better. So if we do much work on the main thread, we could have dropped frames, and this would be not so good about the users of our application. However, we should know that building UI or animations or triggering HTTP requests could not create any junk in NativeScript. However, we should be aware when creating CPU-intensive work through JavaScript, because this would actually create junk. However, the same thing happens in Android. If we were to write Android applications using Java or Kotlin, we would still be using the main thread, the main Android thread. And everything CPU-intensive done would cause junk. So in NativeScript, it's pretty much the same. But what do we do if we actually want to invoke some CPU-intensive functionality? Well, we use worker threads. They're pretty much the same as the ones used in Chrome or Node.js nowadays. And using worker threads, we execute the JavaScript on another thread. Again, this is not by default. We should create worker threads manually by hand. And some disadvantage of worker threads is that there is no JavaScript memory sharing. So we can send messages from one worker to another and vice versa, but we could not share references to JavaScript objects between them. But how is actually the worker thread implemented in NativeScript? Well, perhaps it's time for some theory. We mentioned isolate, but what is it actually, the isolate? The isolate in V8 terms it could be considered as a V8 process. It has one garbage collector, it has a memory manager, and it executes JavaScript. It is not the same as threads in, for example, Java, C# or C++, because in a language with threads can share memory. But in V8, isolates cannot share memory between each other. We can have multiple isolates, but they do not share any memory. And because of that, they could be run in parallel without any synchronization issues. And another thing we mentioned is the V8 context. But what is actually a context? Well, context could be considered as one scope of execution of a JavaScript code. So it does not have any memory isolation, and one isolate can have multiple contexts. Of course, they can't run in parallel. But how do you think a worker thread is implemented internally? Does it use an isolate or context? Who's it for isolate? And who's it for context? Well, if you guessed isolate, yeah, this is the case. And again, when we are building native mobile applications with JavaScript, we want them not only to execute fast, but to start fast. Nobody is going to like our mobile application if it takes 10 seconds to load. Nobody is going to like it. So how do we deal with the startup time? How do we make it fast? Well, let's talk about the startup time and see where these slow paths were. In Android, when we want to make a file system request, well, it's a file system request. It cannot be fast. It's pretty much slow. And it has been observed that, yeah, this is years ago, without many optimizations in the NativeScript runtime, but it has been observed a couple of years ago that starting up our application takes about 2 seconds, which is really terrible, I would say. And we can see that most of the time spent is about different file system requests. And how could we minimize this cost? Well, if we bundle our app and For example, if we have 100 JavaScript files consisting of our business logic of the application, if we bundle it into single files, well, we would have fewer file system requests. So we could fasten up the launch time. And for this, NativeScript uses Webpack. Webpack, as you probably know, bundles our JavaScript code and produces some 2 or 3 files which consist of our bundled logic. But what about the parsing and compiling of the JavaScript? Well, V8 has to parse our JavaScript, interpret it at first, at a later point compile it, and this process is, I won't say slow, but it could be faster. And how could it be faster? We must load the JavaScript at some point, and this is where snapshotting comes into. So V8 has some really nice functionality where we can create a snapshot of our JavaScript. And this happens build time. So when Webpack has produced our bundle vendor.js files, then we trigger the V8's make snapshot tool. What it does is to get the vendor JavaScript, load it, again build time, and create a snapshot of its execution context. After that, we have some snapshots. You can see the .blob files, and we have several of them for the different Android architectures. Some for ARM and some for Intel architectures. After that, when we build our package, the Android APK, all these snapshots are included in it. So when the runtime and the NativeScript application starts, if we see such snapshots, we load them. We do not tell V8 to parse and compile the JavaScript. We load the snapshots. And this is really, really faster than parsing and compiling the JavaScript at runtime. However, there are some limitations. As I said, creating snapshots of our JavaScript code is done at build time. And at build time, we do not have any information about the Android APIs still. As I've said, the Android APIs are configured runtime, not build time. So when we create our snapshots, we do not have information about the Java classes or Kotlin classes, which could have been used in the JavaScript. And what do we do in such cases? For example, if we had some JavaScript code which tried to get the Android SDK version, well, actually trying to snapshot this JavaScript code would fail because the V8 snapshot tool would try to look into the Android object present there, and it would not find it anywhere defined in our JavaScript code. So it would crash. How could we safely make our code being snapshotted? Well, we could be a little bit lazy. Instead of using directly the native API, we could use it from a function or a lambda, like in this case, and the V8 snapshot tool would just see a function or a lambda, and it would not look into its internal implementation. So the code on the right would snapshot without any problems. And I would say, yeah, be lazy regarding using native APIs. As a final note, I should mention my colleague Vladimir Mutafov, who has helped me with this presentation. And yeah, this is it. If you have any questions, feel free to ask them.
Thank you for coming to this conference. So I have a question regarding garbage collector. So you mentioned that in V8 we keep a reference to our object. Yep. And then in the Java runtime we keep another reference to the Java object. Can I say that for each object we are actually consuming twice the memory to store it?
Well, actually, yeah, we store two references, but the one stored in the Java world, in Android, actually this is the bigger one. For example, consider the problem with the images. We may have an image which is, let's say, 2 megabytes large, but these 2 megabytes are in the native Android memory. However, the reference and the object held in V8 is really small. It would be, not sure at what size, but it would be a really simple JavaScript object just with some properties. It would not have any kind of data, so it would be really small. And we think that this is not a problem.
Yeah, and another question would be, say if now I'm finding some problems in my JavaScript app running on NativeScript. How do I know how is the debugging experience? Like, because it's built on top of Java runtime and then NativeScript and then V8. Is it like how good is it?
Yeah, well, about debugging, there are several things you could use to debug your NativeScript application. One of them is we provide a Visual Studio Code extension for debugging your JavaScript, and you could debug it just like any other regular JavaScript. And you could also use the Chrome developer tools in order to debug, again, stepping line by line, just like any debugging of website, for example. And there you could see the memory footprint of the application. But if you run into, I don't know, any performance problems, perhaps for me the most useful thing is the Android Studio profiler. And yeah, with the Android Studio profiler, you could look into the native world, what happens underneath, and you could also debug native code. You could even debug the V8 itself. But this is not something which happens in the everyday use of NativeScript. I mean, this is really rarely happening. So probably, if you want to just debug your applications, Visual Studio Code or the Chrome developer tools are the way to go. You had a question?
I have a question for the marshalling. You mentioned how you do the marshalling for the object between the JavaScript and Java. Do you marshal only the primitive type or scalar type, or you can also marshal in the object? And for example, the datetime in JavaScript and in Java, the datetime is different. So do you do that kind of marshalling? That's just complicated, right?
Yeah. Actually, we marshalize mostly the primitive types. Like I mentioned, those are the number types in Java, and we marshalize them to JavaScript, and of course, vice versa. JavaScript primitive types are converted to Java primitive types. But for your question about date times, actually we have such an open issue in GitHub in the Android runtime, and we are considering implementing it. But yeah, as you said, the JavaScript datetime is pretty different than Java's datetime. And actually, one of the biggest problems is that Java does not have one datetime class. It has the, I would say, at least 3 APIs which are widely used in Java for representing datetime. And as of now, we do not marshalize this, but we have such plans. And if you still want to invoke, for example, some native Java or Kotlin method which receives a parameter of some Java datetime, for example, you could create the datetime object through JavaScript and pass it along. But currently, we do not marshalize datetime objects. Only the primitives types and strings. All other types, objects, are marshalized to JavaScript proxy objects.
我们现场可以再开放最后一个问题，有人还有问题要询问吗？
Do NativeScript provide a user interface API? If it does, how do you manage manage the difference between iOS and Android UI components? If it doesn't, how does developers implement their UI?
If I understood correctly, your question is how do we build the abstractions regarding different Android and iOS APIs, right?
What I mean is because you have in Android and iOS they have two different UI systems, right?
Yeah.
In Android they use views and iOS they use view controllers. And do you wrap them in NativeScript, or do you have your own UI implementation?
Yeah, well, in NativeScript, we provide a common abstraction. This means that we provide only the common things about a native API. So, for example, a NativeScript button is actually implemented. If we are running on Android, it uses the native Android button underneath. If our NativeScript application is running on iOS, well, it uses internally the iOS button element. I'm not sure in iOS what the type for the button was, but yeah, NativeScript abstractions use the existing Android or iOS APIs. So it's kind of different, for example, from Flutter, where in Flutter they have their own view system and actually they draw on some canvas, but they have their own view system. And in NativeScript or React Native, it's not the case. Any abstractions actually use the existing native elements or APIs. No problem.
好，那最后让我们再一次掌声，谢谢 Vladimir。